So we now know that we can represent periodic functions in time using the cosine or the sine if we had liked, but why is this true? Why does the voltage or current in an AC system even look like a sine wave? Why not some other wave shape? Why isn't it arbitrary, or why isn't it a triangle or something like that? Why can we use sine and cosine? Well, the shape of an AC waveform is due to the particulars of the construction of the generators used to produce these voltages. So, at power plants we have AC generators, and these are machines that spin and use electricity and magnetism to produce voltage. And the reason it's sinusoidal is due to the construction of these machines. So AC generators produce voltages by rotating a coil of wire inside a magnetic field, although the particulars of that are different depending on different generators. In general, voltages are produced by rotating a coil of wire inside a magnetic field. So in this diagram, you see we've got a magnetic field, a magnetic south pole, a magnetic north pole, therefore a magnetic field points between those, and we've got this coil of wire in between it, right? And we're going to rotate that coil of wire. The voltage produced by the generator will reach a maximum value when the coil is parallel to the field in one direction. So that's indicated here in figure B. We see that the coil has rotated parallel to the field, and we get a maximum voltage in one direction. The field will go to 0 when the coil is perpendicular to the field. So we see in A and C, the coil has rotated to be perpendicular. In both cases, the voltmeter we've got hooked up here is indicating a 0 value. And the voltage will reach a minimum, which is actually a negative peak, when the coil is parallel to the field in the opposite direction. So in diagrams A and C, the coil is perpendicular to the field. 0 volts are flowing or are measurable across the terminals of this coil. In figure B, the coil reaches a peak positive value, and in figure D, the coil reaches a peak negative value. And in between those, we have to kind of imagine that we can see this coil rotating, and what is happening is the value of the voltage is increasing as the coil rotates from position A to B. The value of the voltage decreases down to 0 from B to C, and then the value of the voltage decreases even further from 0 to its negative peak as it rotates from C to D, and that's kind of what we're showing here in this graph. So what we see is that if the speed of rotation is held constant, the voltage produced as the coil of a wire is rotated through the field takes on a sinusoidal shape. So as long as we spin this thing at a constant rate, we can see that the value of the voltage, it goes from here at A to here at B to here at C to here at D, back to here at A, and just would repeat itself, right? Because it's cyclical. And in between those, because it's rotating in a circle, we get this nice sinusoidal shape. All sinusoidal functions are specified by 3 parameters: amplitude, frequency, and phase. Amplitude, frequency, and phase. So if we have a sine wave, we can specify it in terms of those 3 terms. And if we were going to write that out, that's A sine of omega t plus phi. That's the general format for a sine wave. Amplitude is the maximum value or height of the curve measured from the neutral position. This is also called, or often called, the peak value. Less commonly, though, the peak-to-peak value is stated, which gives the total value from crest to trough, or twice the amplitude. So if we look at this amplitude chart, we've got this blue line indicates y equals sine of 2 pi x. What we're interested in here is just the amplitude. We'll notice that the amplitude of this one is 1. The amplitude is A here, right? And here it's a 1. It's inferred to be a 1. And we see that the peak occurs at 1 and the negative the min occurs at -1. So a sine wave of amplitude 1 has a peak value of 1 unit. It has a peak-to-peak value of 2 units, right? Here in the green in the same box, we have a sine wave that's got an amplitude of 0.5. That means its value from the 0 axis as measured to its maximum positive point is 0.5 units, 0.5 volts, 0.5 amps, whatever it is happen to be measuring. The peak-to-peak value, the value from here to here, is therefore 1. It's 0.5 from here and 0.5 down from there. So that's the amplitude. Next we'll look at phase, or sorry, excuse me, frequency. Frequency is the number of complete oscillations per unit time, and like we said before, is measured in cycles per second or hertz. 1 hertz is 1 complete oscillation in 1 second. So we say 1 hertz is 1 cycle in 1 second, right? A hertz a cycle per second. An alternative method to stating the frequency is to use its inverse, or the period of the waveform, right? Where the time, that's the time taken to complete a cycle per oscillation, measured in seconds. Frequency is also measured in radians per second, as in angular frequency, and like we said before, is given the Greek symbol lowercase omega. Omega equals 2 pi f for the frequency. So here in this frequency graph, we have omega specified as 2 different numbers. We've got omega is 2 pi, and we've got omega is 4 pi, right? So those are, in this case, x is going to be measured in seconds. So we multiply 2 by second. So this is in radians per second, and that's in radians per second as well. So what we see is we've got a 2 pi, that's 2 pi radians per second is this blue. So it will cut out 1 radian per second. So we'll see that the blue line every second will transverse 2 pi radians. And the green function has a frequency that is twice that, or 4 pi, so every second it will cut out 4 pi radians, or it'll do a complete transversal in half a second. And so we can see that here, right? If in 1 second, which time's on the x-axis here, if in 1 second we go 2 pi, we should see 1 complete oscillation at 1 second, as indeed we do. And then if we look at this green plot, we see that the angular frequency is 4 pi. That means it does 4 pi radians in a second. That means it should take half a second to do 2 pi, or 1 full rotation. And so if we plot out 1 period, it should only take half a second. And indeed it does. So we see that increase in frequency, you see more peaks per second, basically. All right, clear this slide real quickly. The last thing that we're going to talk about is, let me write that. We've got a sine of omega t plus theta. You'll see that sometimes theta is used, sometimes phi is used, kind of interchangeably right there. Phase, in this case, I'm going to use the lowercase symbol phi, represents a delay from the original starting point of a sine or cosine wave, or a separation between 2 sine or cosine waves measured in degrees or radians. This can also be thought of as the angle by which the sinusoid is displaced ahead of or behind of where it would have been had it started at time 0. Graphically, what this means is it manifests as a shift of the entire curve, either left or right. Sine and cosine have a phase difference of 90 degrees, and a lot of times we'll say that they are 90 degrees out of phase, right? There's a timing difference there. So here in the phase plot, we've got 2 plots. We've got the standard plot of sine of 2 pi x, so that's this guy, right? And that means here this is time 0. So it started at time 0. What does the sine of 2 pi x minus pi over 6? A minus pi over 6 means we've shifted the sine function pi over 6 units from where it would normally start. So that distance, the frequency separation there is going to be equivalent to pi over 6. So we see that a minus pi over 6 shifts the graph to the left in phase, where a plus pi over 6 would shift the graph, sorry, a minus pi over 6 shifts the graph to the right in phase, delays it. A plus pi over 6 would shift it to the right. So it just represents a change in where the sine wave starts.